Hello everyone, welcome back to my YouTube channel Unfog with Dr. Tahar Parvin. In this class, we are going to discuss last part of modern physics based on Hstr syllabus. Before starting the class, I want to remind you all, please do subscribe to my channel if you have found my channel just now and if you are watching my class for the first time. And who are already subscribers to this channel, all the teacher recruitment aspirants, Hstr, GPSTR, TET and all such competitive examinations, please do share my classes based on physics and mathematics among other aspirants and your friends for more such free video classes. Okay. So let us start the class by continuing from where we have stopped in previous class, that is class part 4A of modern physics. Now let us continue, and this class is also a free class in my YouTube channel, and of course notes will be given to paid class aspirants, and this will be the part 4B class of modern physics. Okay, let us start with the multiple choice questions. Later let us proceed towards mass defect and binding energy, and then we will solve problems based on mass defect and binding energy, and also a few theoretical multiple choice questions also we will be solving. All those questions are very important and expected questions. Okay, so please do watch full class carefully and try to make notes also if you are not a paid aspirant. Okay, if you are a paid aspirant, then you will be getting the PDF of this class. Okay, so let us start the class. Few simple multiple choice questions we will discuss. Again, we will go to the next topic. Okay. Now, simple questions means they can be like this. What does C stand for in equation E is equal to mc square? Very easy question anyway. But then I thought that you never know. They may ask a simple question also. They may ask tough question also. So we need to be ready with all levels of the questions, right? Easy, medium, hard. Okay. But then hard will not go to next level. That also you should know. Okay. So what is C here in E is equal to mc square? Of course, it is speed of light. Okay. So option D will be the correct answer. Next question number 2. According to equation E is equal to mc square, what happens to the mass of an object if its energy increases? I told you, right? See, E is equal to mc square is there. What is there in the question? They are telling what happens to the mass of an object if energy increases. So our aim is to maintain E by m as c square. So if E is increasing, m should decrease. Correct? So option A will be the correct answer. You don't even need to see the other options also. In some questions, you don't need to see options because those options will confuse you. When you know the concept clearly, just go for the correct answer. Okay, don't see other options. Okay, so here when energy increases, obviously mass of the object will decrease because our aim is to maintain the value of E by m as c square. Okay. Next question. How is the equation E is equal to mc square related to nuclear energy? Option A, it explains the principle behind nuclear reactions. Option B, it is not related to nuclear energy. Option C, it is a fundamental equation in nuclear physics. Option D, it was first discovered in a nuclear power plant. So, which one is the correct statement related to E is equal to mc square and nuclear energy? I have given you the example, right? In nuclear reactions, nucleus of an atom will split into two or more smaller nuclei and enormous amount of energy is released. Now this energy is released because mass of the resulting nuclei is very less than the original nucleus. And this difference in mass is converted into energy. And this is going according to E is equal to mc square. So the principle E is equal to mc square is behind the nuclear reactions. So option A will be the correct answer because nuclear energy or nuclear reactions, they obey E is equal to mc square. Okay, this they obey this. Okay. Next question. The mass and energy equivalent to 1 AMU respectively is. Now, as we have already derived it, we know the values now, right? The mass equivalent to 1 AMU is 1.67 into 10 to the power minus 27 kg, and energy equivalent to 1 AMU is 930 MeV. So, because we know these values, it became easy for us to answer this question, right? So, I advise you to please remember these values, okay? 1.67 into 10 raised to minus 27 kg and 930 MeV. So, option B will be the correct answer. Now they can ask a simple question like this also. Mass equivalent of 931 MeV energy is. Now in E is equal to mc square. I know that if that mass is in 1 AMU, the mass is 1.67 into 10 raised to minus 27 kg. In that situation only I will get E is equal to 931 MeV. Now I will not do any calculation, just I will take the correct answer. 7 is not there, 6 is there, approximately it is a option D is the correct answer. Okay. Next question. The equivalent energy of 1 gram of substance is. Now I think you will have to calculate, because options though are the good only, but then there are chances of making mistakes. So because the mass which we are using every time is in kg, right? So what you do now, what is mass? Mass is equal to 1 gram, or you convert it into kg. It will be 10 raised to minus 3 kg. Correct? C we know it is 3 into 10 to the power 8 meter per second, or if you do square, C square will become 9 into 10 to the power 16. Correct? Now you use E is equal to mc square. What is there in mass? It is 10 to the minus 3. And what is there in place of C square? It is 9 into 10 to the power 16. Your answer will be 9 into 10 to the power 13 joule. This is your correct answer. Option F will be the correct answer. Okay. So, because I am solving this type of problem first time, so I am writing everything clearly. Okay. Once you all learn, you don't need to waste your time in the examination. You are sure, means just go for the correct answer and then proceed with the next question. Okay. Now let's talk about another concept, mass defect. Mass defect means, as name only indicates, it is the difference between the atomic mass and sum of its constituents masses. See, there is one atom. It is having many constituents. Many things are there in that. If you check the mass of this atom and the constituents together, total mass, it should be equal, right? But it is not equal. It is not coming out to be equal. There is some difference. This difference is known as mass defect. Okay. So, the difference between atomic mass and some of its constituents masses is known as mass defect. And how do you represent it? You represent it by delta M, because there is some change in mass, right? To show that there is change in mass, you represent it by delta M. And the formula, obviously what will be the formula? The formula for delta M or mass defect should be your total mass of constituents minus mass of atom. Correct? This only should be there, right? So that only we are writing it like this. So no need to get scared by seeing the formula. What is there? Number of protons into mass of proton, and number of neutrons into mass of neutron. That only is there in a nucleus, right? So if you are adding all that and then subtracting it with the mass of the atom, then you will find some change in mass. Okay, that is your mass defect. If you want, you can also see things here. See, actually electron mass is negligible. See, electron mass, it is very much negligible when compared to proton and neutron. This is the reason why we are considering proton and neutron. Okay, even if you include electron also, there will be change in the mass. Then also it will be there. Okay, you may ask this question, madam, you are not at all including electron. That's why you are getting mass defect. It's not like that. If you include mass of electron also, you will get mass defect. Okay, anyway, because the value, the mass of electron is negligible. No, that's why we are not including it, because things will become again complicated, right? That's why. So here in this formula, A is atomic number, Z is mass number, and M of proton means mass of proton, M of neutron is mass of neutron, M of atom is mass of atom. Okay, so mass defect will be equal to Z into M proton plus A minus Z into M neutron minus mass of atom. Means this together, no, this whole thing together is mass of constituents of atom. Okay, I hope you are getting now. Okay, so this will make it easy for you to remember this formula. Okay, I have brought one example, like I told you, the same example I am putting it with the helium here. You can see that mass of helium is so much, 4.00260 AMU. But if you see the constituents, see, you are taking 2 electrons, you are taking 2 protons, you are taking 2 neutrons together. Everything if you are saying means there is some difference. All both values are not same. Okay, this is known as mass defect. Okay, mass defect. But another important point is that this mass defect can be portrayed in the form of energy also, because it is responsible for binding the nucleons together. What are nucleons? Means the constituents of nucleus. Okay, from Einstein's mass energy relation, you know that E is equal to mc square. Correct? So from this concept, this mass defect is nothing but the energy. This energy is the actual binding energy, means the energy between the nucleons, because of which that nucleons are together. Okay. Now what are nucleons? Means now I have given this figure also. You can understand what are nucleons. The constituents of nucleus are nucleons. What are they? They are protons and neutrons. Together they make up this atomic nucleus. But why are they together? They are together because of this mass defect or binding energy. So now I can synonymously use mass defect as binding energy, because energy equivalent to that of mass defect is nothing but your binding energy of the nucleus. Now binding energy means energy, right? What is energy? It is mc square. But it is not just mc square here. Binding energy will have mass defect. Okay, I don't need to write E again here, right? So binding energy will have product of mass defect and the speed of light whole square. That is your binding energy now. Okay. Now mass defect thing, so we have this formula, right? mp into z plus m into a minus z minus m. This is your mass of the whole atom. Okay. So that into E square. Basically I am substituting delta m. Okay. But if I want to find the binding energy per nucleon, for one nucleon how much binding energy is there? Means the average energy required to release one nucleon from nucleus. I want to remove that nucleon from nucleus. How much average energy is required? That is your binding energy per nucleon. So this one will be equal to total binding energy upon mass number. Okay. See, binding energy per nucleon will be equal to total binding energy upon mass number. Okay, now what is binding energy? This we have saw it, right? It is delta m into c square. What is mass number? It is capital A. I told you while deriving the value of energy that E is equal to 931 MeV, right? And synonymously we use it for c square also, right? When you want to neglect the mass. So delta m is very, very small here. So what I can do is I can write this binding energy per nucleon as 931 here, and delta m, if I want, I will write it as it is there. I have A. Okay, so that will be my value for binding energy per nucleon. And what will be the unit? It will be MeV. Okay, and another important point is that this binding energy per nucleon is directly proportional to stability of nucleus. This is very, very important. So we plot a graph based on this binding energy per nucleon also. I have the graph here. You call it as binding energy curve. This is a very, very important curve because if they want to ask any question from binding energy, there are more likely chances that they ask question from this graph. Okay. Basically, binding energy curve means it is graph between binding energy per nucleon and total number of nucleus. What is total number of nucleons? Total number of nucleons means nothing but mass number, right? Number of protons plus neutrons is the mass number, and number of protons plus neutrons are nothing but the total number of nucleons in the nucleus. So you put that mass number in x-axis and you put binding energy per nucleon on y-axis. Then you take few atoms, few elements, and then you check their binding energy. Here you can see that there are some nuclei with mass number less than 20. They have large binding energy per nucleon. Okay. When you compare with their neighboring nuclei, the nuclei which are portrayed here, no, hydrogen is there, helium is there, the isotopes of hydrogen are also there. Isotopes of hydrogen are there, lithium, nitrogen, oxygen, carbon, sulfur, iron, all those things they are plotted here, right? Here you can see that who are having atomic mass, mass number less than 20. They are having large binding energy. Okay. And of course, the graph will reveal many things. That all I will tell you. Only one thing which I wanted to tell you is these examples of these These are the nuclei which are more stable than their neighbors. Okay, why? Because of this binding energy only. Because that binding energy per nucleon, the fraction will give you stability for that particular atom. Okay, that is the reason. Okay. Now, what is the importance of binding energy curve? The very small nuclei will tend to fuse together to form one heavier, more stable nuclei. That can happen. All these things are linked with the radioactivity, nuclear fission. Okay, radioactivity and nuclear fission. Now, larger nuclides like uranium, they will have tendency to, you can see here, they will have tendency to split into two smaller nuclei. This is your nuclear fission. Okay. And of course, this process will require some kind of trigger also. But then this is happening, right? This is happening because of binding energy only. The larger nuclides will show some phenomenon of radioactivity also. Okay. So that is the main reason. One thing you can say is that these are here mass number is less than 20, right? For this, you can see that it is increasing. Fully it is increasing. Again, it will increase here also. This will be actually iron, it will be. I'll show you the graph again. Here you can see that it is very gradually decreasing. No sudden thing is happening. So, sudden thing is happening only till this range only. Correct? After that, suddenly it is not increasing. Now, what are the observations based on this graph means? Firstly, we have binding energy per nucleon will increase sharply with mass number up to 20. This I already told you, right? Next, after mass number 20, it will increase slowly. Then you can see some recurrence of peaks are there, not for all elements, for all atoms it is not increasing. For few mass numbers it is increasing. But what are the mass numbers for which this binding energy per nucleon is increasing? Means they are multiples of 4. They are multiples of 4. You can see 4, 12, 16 like this. 4, 12, 16, 32, 56 all are multiples of 4. Correct? They are multiples of 4, and for this only that binding energy per nucleon is increasing. You can see here in the graph if you want. Okay, I will not overwrite because you cannot again read properly. No, you will not be able to see properly. That's why I am not overwriting, or else I will show here like this. You can see that here what are the elements it is increasing. It is for helium it is increasing, for carbon it is increasing, for oxygen, for sulfur, correct? They are all having mass numbers which are multiples of 4. Okay, and also they are containing equal and even number of protons and neutrons in them. That is also one speciality. Okay, only for those atoms the binding energy per nucleon is continuously increasing or sharply increasing. These are the examples I have already told you, right? Next is binding energy per nucleon will reach a maximum of 8.8 MeV at one particular mass number 56, which is your iron. Iron. Very, very, very important question. They may ask as a MCQ. Okay. Now this energy, here what will be the energy also, that binding energy per nucleon, the value will be 8.8 MeV. What is the mass number for iron? It is 56. Okay. Now this is corresponding to nucleus of iron. So iron nucleus is the most stable nucleus in the periodic table, you can say. Okay. And also this also you have to see that here in this range, the blue box I have put, this region is of greater stability. Here you can see that the elements falling in this range, they are comparatively more stable and they are non-radioactive. Okay. Here the binding energy falls in this range, 8.5 MeV. Okay, 8.5 MeV. So all these values are remembered. Basically, I think you can remember the value 8. That will be helpful. Okay. The value of 8 MeV for binding energy will be helpful. Okay. And what is the mass number for greater stability region? It is lying between 40 and 180. Okay. Now let us discuss many more multiple choice questions. All these are expected questions. Okay. The question number 7. The nucleus of which of the following atoms whose atomic mass numbers A are given in the options would have the highest binding energy per nucleon? So, among the 4 options, which will have the highest binding energy, you have to see. You can easily see here that atomic mass number 100 is having a better stability, because see, we have to choose from 200, 100, 5 and 20, right? So in that, if I see, this is having more stability. So molybdenum. So option 2 will be the correct answer. Okay. So you should learn this graph nicely. Next question is the highest binding energy per nucleon will be for. So wherever iron is there, no, don't worry. Just take the correct answer as iron only, because highest binding energy is for iron only. Whatever the other options are, you don't see. Even uranium is also you don't see, because you see the graph, uranium is having less binding energy per nucleon when compared to iron, right? So iron is the correct answer. In fact, iron is the one atom which is having the highest binding energy among all. Okay. Next question. Which isotope below has the highest nuclear binding energy per gram? So if you see the options, the mass number is more for uranium, but we know that uranium will have less binding energy per nucleon. So who is near iron, that you have to see. Mn is near iron. See the mass number, it is 55, right? So for iron it is 56, right? So it will be near iron only, Mn. So that will be the correct answer, not uranium. Okay, you have to remember this. Next question. Nuclear binding energy is equivalent to, of course, it is equivalent to mass defect of nucleus. This you should remember only now. Okay. So I hope if you are attending the class carefully, means then you will remember this. Okay. Binding energy is nothing but the mass defect of nucleus. Mass defect for the helium nucleus is 0.0303 AMU. Binding energy per nucleon for this is in MeV, will be. In MeV, what will be the binding energy they are asking? See here, mass defect is given, delta M is given. Binding energy, we know that it is equal to delta M into C square. Okay, we neglect mass and we directly assume that C square is equal to E in E is equal to MC square thing. So I can write it as a 931.5, you write, it is up to you. Or you can also write it as 930 also. Just 930 also you can write, just to make things easier in calculation. Then you substitute delta M, they have given, right? You put it here and this thing is there, multiply. Once you multiply, you will get binding energy 28 MeV. But then they are asking for helium nucleus. So how much is the mass number for nucleus? It is 4, right? 2 neutrons, 2 protons. This you should remember, you should not forget, because we have talked about this in alpha particle scattering also, right? Rutherford's alpha particle scattering. We are told that the alpha particle is nothing but a helium nucleus, remember? So it will have 2 neutrons and 2 protons. So helium nucleus is having mass number 4, or number of nucleons are 4. So I need to divide this binding energy 28 by 4. So my answer will be 7 MeV. Okay. So you need to calculate things here. Actually 0.0303 into 930 also you can do. You will get the correct answer only. It will be 7 MeV. Okay. Next question. The energy required to break a nucleus into its individual nucleons is called. See, I have told you. What is the energy required to remove one nucleon from the nucleus? I told you, right? That is nothing but your nuclear binding energy. Option A should be the correct answer because it is the energy required to break a nucleus into its individual nucleons. Okay. So this nuclear binding energy, you can also define it in another way also. It is defined as energy released during formation of hypothetical nucleus from its protons and neutrons. See, the binding energy is both. Either you are removing nucleons, okay, or you say that some nucleons you are making them to fall in their place. Means you are putting back in nucleus, you think. Okay. At that time also energy is released, right? So whatever energy is required to remove or put back, that is your binding energy or nuclear binding energy. Okay. Next question. A nucleus has a mass number A, atomic number Z and a binding energy B. The mass of neutron and proton are m and nmp respectively and c is the speed of light. Which of the following expressions correctly represents the mass of the nucleus? See, don't see the options. Okay, I will explain you how to find the answer. See, we know that binding energy is equal to mass defect into c square, right? With this, I can find delta M as binding energy upon c square, right? Now, what is mass defect formula? Remember, it is something like this. A minus Z into Mn plus Z into Mp, the constituents of atom minus mass of atom. Like this, right? Now, in place of binding energy, I mean mass defect, I can write it, right? I can write binding energy upon c square, right? So, this will be equal to A minus Z into Mn plus Z into Mp minus mass of atom, total mass of atom. Now, what is the question? They are asking you to find the mass of the atom or mass of the nucleus, because if I write nucleus here, that is also valid because I am neglecting electrons, right? So, I can write nucleus here because I am not using mass of electrons here. In both cases, while I am writing mass of atom also, I am not including the mass of electrons, right? I am neglecting that. Anyway, now mass of the nucleus, if I put it in the left hand side, what will be my answer? It will be A minus Z into Mn plus Z into Mp minus binding energy upon c square, right? So, which one will match here? You see, option A, this one will match. Okay. So, this is the correct answer. Same type of question they can twist and turn and ask. Answer will be same. You have to understand the question and you have to solve it, or without solving also you can remember this equation also. Okay. Next question. What is mass defect? So you have to read out the options very carefully and then you have to answer the question. You know the definition of mass defect. It is a difference between mass of an atom and sum of the masses of its protons and neutrons. Okay. So option B will be the correct answer. Next, which of the following is true about the relationship between mass defect and nuclear stability? Now here what you have to understand is that having mass defect more means stability will be less. Correct, right? More mass defect means the stability will be less. Less mass defect means stability will be more. Okay. Or I will write like this. Your mass defect will be inversely proportional to stability. Because mass defect is a bad quality, right? It is a bad quality of an atom. So this will, if the mass defect is increasing, this will decrease the stability. Correct? The atom will not be stable. So higher stability if you need means your mass defect should be less. So option B is the correct answer, because more stable nucleus will require less energy, because less energy is needed to hold that constituent particles together. Means your nucleus is stable. If nucleus is stable and is having less energy means mass defect is less, because mass defect is nothing but binding energy, right? See, mass defect is nothing but binding energy, right? So if binding energy is less means obviously the meaning is mass defect is less. It means that the atom is stable. Okay, higher mass defect will imply nucleus is less stable because it will require more energy to hold its particles inside the nucleus. Okay, so lower mass defect, higher nuclear stability. This you have to remember. Okay. Next question. If M, A, Z, MP and Mn denote masses of the nucleus X, proton and neutron respectively in units of U means AMU, and binding energy represents its binding energy in MeV, means BE represents its binding energy in MeV, then so this one we have already done here. You don't need to worry, we have already done it, right? Only thing is here you should not get scared by seeing this, because they mean to say that it is a mass of a nucleus. Okay, so this is a mass of this is nothing but mass of nucleus. Okay, or you can also say that it is mass of atom also. If you neglect the electron, you can also say that it is mass of atom also, because we are what we were writing mass defect as equal to ZMP plus A minus Z into Mn minus mass of nucleus. No, so this mass of nucleus you can write it like this also. This is mass number and proton number, like this. Okay, so that is the same thing. You don't need to worry with the symbols and all that. So you put it in the left hand side, you put it like this in the left hand side. Now this is equal to VE upon C square, right? So this thing you put it in the left hand side and this thing you put it in the right hand side. Same answer you will get as you got before, that is option 1. This only is the correct answer. Correct? This only we got now last time also, minus BE upon C square. Okay. Next question. How does the binding energy per nucleon vary with the increase in the number of nucleons? This is very interesting. See, you see the figure. The number of nucleons, no, if you see binding energy per nucleon, the binding energy per nucleon, first it will increase and then again it will decrease. Okay, this is all happening with increase in mass number. See, mass number is increasing, right? But binding energy, it is first increasing, then it is decreasing. That too, it is increasing sharply, but it is decreasing little gradually. The speed became less, right? So, how does the binding energy per nucleon vary with increase in number of nucleons? You have to say that first it will increase and then it will decrease with increase in mass number. Option D will be the correct answer. Okay. Now they can ask very simple questions also, you never know. Okay, that's why I have put very simple questions also. The term relativistic refers to the effects that are, of course it is nothing but the effects that are when observed when speeds are near the speed of light. That's the reason why we are using E is equal to mc square, right? Anyway, I did not go into detail because I didn't want to trouble you all, because that was not there in the syllabus. But then you should know this very simple concepts also. That's why I've included these MCQs, so that you will get some idea about these points also. Okay. Next, which of the following is Einstein's mass energy relation or mass energy equivalence? All that will be there. Two names also will be there. That is E is equal to mc square. Okay. What is the cause of mass defect? Of course, binding energy. The cause of mass defect is the binding energy. This will hold the nucleus together, and this is the energy which is required to overcome electrostatic repulsion between positively charged protons in the nucleus. That also you can say. Okay. Now this energy is released when nucleus is formed and is equivalent to the mass defect. All points came here. Okay. Even electrostatic repulsion also I put here because you never know what type of question they ask. But this is very general topic. Even we can teach this topic to a 9th standard child and to a 12th standard student also. So very general topic. But I don't want to go in the next level. That's why I'm trying to stick in the medium range as much as possible. Okay. Now we discussed all that mass defect, binding energy and binding energy per nucleon. This was there in the syllabus. But packing fraction was not there in the syllabus, but somehow I did not feel to skip it. That's why I am telling you 2-3 points about packing fraction also. Now what is packing fraction means? It is nothing but mass defect per nucleon. Now binding energy per nucleon we did know. Like that only mass defect per nucleon is a packing fraction, and the formula for packing fraction is m minus a upon a. M is actual isotopic mass and A is mass number, that you know, right? So many atoms are isotopes also, right? So you can take the actual isotopic mass m, or you just remember it as a mass of the atom also, if you don't want to get confused. Okay, so that is one mass of the atom, and this is mass number. You have to subtract it in the numerator. Denominator you just have A. Okay, so you never know, they may ask some simple question on this. So I have framed 1 or 2 questions on packing fraction also. Like for example, this is the one. The mass defect per nucleon is called, of course, the mass defect per nucleon is called packing fraction. The correct relation between packing fraction and mass number is, it should be m minus a upon a. Option A. So I thought that I should not skip packing fraction. Somehow I get scared sometimes, because though they are not giving in syllabus, because it is related to mass defect, right? And they have given mass defect in the portion. So that's why I am giving you some simple points on packing fraction only. I have given only 2-3 points I have given. Outside of this, though, they will not ask for sure. So this finishes your modern physics chapter. I really hope that this class helps you. And before signing off, I want to remind you all, please do like, share and subscribe to my channel for more free classes, because if there are many aspirants who are present in my channel as subscribers, then maybe in future I can give more important classes based on Hstr syllabus for both physics and mathematics. Okay then, thank you, all the best, bye.